Hello everybody and welcome to the second lesson, and I hope we'll be happy handing. Where we left off, I think before started, let's review what we have done on the previous lesson. As you remember, I teach you divisibility with properties such as two special theorems, which are Fermat-Little's theorem and Fermat theorem, and after that I have solved 6 questions and we have end up. And today I'm willing to teach you another parts such as prime, composite numbers, squares, cubes. Of course, to understand and observe better, we have to practice so much. Okay, anyway, I would like to finish my speech and let's use our time wisely. Let's start it. Okay. We have finished part A yesterday, and today we will continue with part B. And B is prime and composite numbers. Prime and composite numbers. Let me give you the definition first. A natural number, by the way, you can write it. Let's write at the same time. A natural number which has exactly two divisors or two factors, it's same, such as 1 and itself. Okay, it's called a prime number. And otherwise, if the natural numbers have more than two divisors, they are called composite, but instead of that we can write just otherwise is called a composite number. Okay. So for the prime, what is the smallest prime number? And also this number is even number. 2, right? 2 is the smallest prime number, and also 2 is even number. And after 2 comes 3, 5, 7, 11, and so on. The numbers are prime because these numbers have just two divisors in itself. 2 is divisible by 1 and itself, and 2 has just two divisors, two factors. 3, 5, same, 11, and the other prime numbers are also same. They have just two divisors, 1 and itself. What about 1? 1 is also has two divisors, 1 and itself. But here, 1 has two same divisors. Must be different divisors. So 1 is not prime number. For the composite number, for example, let me take one even number, 6. 6 is divisible by 1, by 2, by 3, and by 6. So 6 has just 4 divisors. So 6 and a composite number. Okay. And for the prime numbers, notice that the smallest prime number is 2. After that comes 3. If the prime numbers are greater than 3, the numbers will be represented by 6k plus minus 1, and 4k is an integer. For greater than or equal to 5, the numbers will be 6k plus minus 1, and k is an integer. K is an integer. For example, for k is 1. 6 times 1 plus 1, 7 prime. 6k minus 1, 6 times 1, 6 minus 1 is 5. It's another prime number. Okay. So we can say if the prime numbers are greater than 3, the numbers will be represented by 6k plus minus 1. Okay? Can we continue? Just say go. That's enough. Sure. Okay. How would it go yesterday? It was okay for you? Okay. Great. By the way, I'm a good cleaner. Okay, now we can have a look at the questions. Yesterday we have finished exercise 1, and today we will start exercise 2 after prime and composite numbers. At exercise 2, question 1. Find all prime numbers. Find all prime numbers p such that 2p squared plus 1 is also prime. Okay. You have got a bit of time to think about it. By the way, I will check my solution. Yeah, here it is. We know that for prime numbers, there are 3 conditions. 2, 3, and greater than 3. But for greater than 3, we have to use 6k plus minus 1. Remember that. Okay. And as I said, 3 conditions. 3 conditions. Depends on p, prime number, p. And on the question we have to prove for all prime numbers, 2p squared plus 1 is also prime. Okay. 4p is 2, 4p is 3, and 4p is 6k plus minus 1. Okay. 4p is 2. 2 times, all you need to do is write in the place of p is all these values. So we can start with 2. 2 squared is 4 times 2, 8, plus 1 is 9. Is 9. For 3, 3 squared 9, 9 times 2, 18, plus 1 is 19. For 6k plus minus 1, let's say for 6k plus 1, for 6k plus 1, it will be 2 times 6k plus 1 square plus 1, which means, let me write directly, 3 times divided 4k square plus 8k plus 1. So means if the prime numbers are greater than 3, 2p squared plus 1 is equal to 3 times 24k squared plus 8k plus 1. And as you see here, for greater than 3, the prime number here is divisible by 3. So it can be prime number, right? So we will not take this interval and also this. For 3, 2p squared plus 1 is 19. 19 is a prime number. Okay. Find all prime numbers, just 3. Okay? Is there anybody question here? Did you get the point? Okay. Have you ever seen before number theory? Yeah, I mean, did you practice before? Or is it the first time? Practice before, okay, Christina. What about others? I have a bit. Mate says, okay. Yesterday I sent the file your teacher. That's what am I gonna do today? Did you take it? We didn't receive it, but I sent your teacher. I sent it. Actually, maybe they forget it, no problem. Stay calm. Okay, let's move on. Okay, as find all prime numbers. Find all prime numbers P, Q, R such that P to the power of Q plus Q to the power of P is equal to R. We have to elevate here as all possibilities. Consider all possibilities for P, Q, and R. Try to do something, please, first. Examine it. Okay, let's solve it. Before solve it, actually, there's something else you should know. When we add two odd numbers, odd plus odd will give us even. Keep it first. If p to the power of q and q to the power of p is odd numbers, r will be even, but says all prime numbers for p, q, and r. So r cannot be even, must be prime. R can't be even. So mono p and q must be even. Because even plus odd is odd. If p, q are primes, either p is equal to 2 or q is equal to 2. Because 2 to the power of any number will be is even, right? For p is 2, 2 to the power of q plus q to the power of 2 is equal to r. And from here, we will get for q and r, for q is 3, 2 to the power of 3 is 8, 3 squared is 9, 8 plus 9 is 17. We will get for r is 17. If p is 3, 3 to the power of q plus q to the power of 3 is equal to r, so we will exchange the values between p and q. Now q is 2, but r remains same, is 17. Yes. We found p, q, and r. P is 2, q is 3, r is 17, and p is 3, q is 2, and r again 17. Okay. Write it down, please. Today, how is my quality of voice and the camera? Is it okay? Yes, it's okay. Master. Okay, yes. Eva, thank you. Angela, yes, thank you. Zehra. Zehra hoş geldin. Nasılsın, iyi misin? Matey, yes. Orhan Baba, yes. Can we skip this part? What do you say? Okay. By the way, I can write next question. Okay. Let P be a prime number greater than 5. Greater than 5. Prove that the equation x to the power of 4 plus 4 to the power of x is equal to P has no solution in integers. Okay, in integer sets. So let me simplify it. X to the power of 4 plus 4 to the power of x is equal to P, and P is a prime number greater than 5. And we have to find the value of x, but says if P is a prime, in this expression for x's, there are no solutions in integer sets. Give a look at it. In this question, you don't have to take too much upon yourself. Just think simple. You can prove later for 6k minus 1, no problem. Okay, so here, just as I told you, just think simple. Try not to think complex. I will show you now step by step. And please pay attention. If P is prime, that greater than 5, so P is an odd number. P is an odd number. X is also an odd number because for X is even to the power of 4 is even, 4 to the power of even is even. When we take the sum of two even numbers, we will get even instead of odd, but P is a prime. So X is also an odd number because I want to show you with details. Odd to the power of 4 plus 4 to the power of odd number will give us odd number. Great. So for X is an even, that's contradiction. That is contradiction. Till here, is there another problem? Is it well? Okay. So for X is 1. So for X is 1. P is 5. P is 5, right? But on the question size, P is greater than 5. So X cannot be 1. For X is 1, no solution. Okay. For X is 2, 3, 4, 5, 6, instead of that, we defined X is an odd number. If X is an odd number, instead of X, we can write 2n plus 1. 2n plus 1. N is element of natural numbers. For example, for n is 1, 2 times 1 is 2, 1 plus 3, right? For x is 2, also P is a prime. Not prime, of course, it's even. So for x's, we will use 2n plus 1. X to the power of 4 plus 4 to the power of x. Instead of x to the power of 4, we can write x squared to the power of 2 plus 4 to the power of, instead of x, we can write 2n plus 1. I didn't use here for x is 2n plus 1 because I will try to factorize it. Is equal to, remember a squared plus b squared. What is it? A plus b squared minus 2ab. The same. X squared to the power of 2 and 4 to the power of 2n plus 1. So x squared to the power of 2 plus 2 to the power of 2n plus 1 to the power of 2 is equal to a plus b square. A is x square, b is 2 to the power of 2n plus 1. First we will take the sum of x square and 2 to the power of 2n plus 1 square minus 2 times x square times 2 to the power of 2n plus 1 equals x square plus 2 to the power of 2n plus 1 square minus, I will try to use here difference of two squares. So for 2 is the root of 2, for x square is x. Thank you very much. For 2 to the power of 2n plus 1, I will write 2 to the power of n plus 1 over 2 to the power of 2. The root of 2 square is 2. X square will give us x square, and 2 to the power of n plus 1 over 2. When we take square of it, we will get 2 to the power of 2n plus 1. So it is difference of two squares, a square minus b square. And what is a square minus b square? A minus b times a plus b. So we write here, over here, x square plus 2 to the power of 2n plus 1 plus the root of 2 times x times 2 to the power of n plus 1 over 2 times x squared plus 2 to the power of 2n plus 1 minus the root of 2 times x times 2 to the power of n plus 1 over 2 is equal to p, which means prime. So p has two divisors and 1 and itself. So p here has more than two divisors. So in this case, p cannot be prime number. So p is not prime. P is not prime number. Where is it? What is that on the 2 that looks like an F? I cannot understand what you mean. Okay, first write it and after that we will discuss, okay? Recai Bey, görüntü ve ses kalitesi nasıl, iyi mi? Okay, Master, now I want to take your question. What is that on the 2 that looks like an F? I'm confused. Where is it? In the last line, you used it 2 times. It is root. That one, right? X squared plus 2 to the power of 2n plus 1 plus the root of 2, root 2. Okay. Okay, let me write here the next part. Squares and cubes. The part B is over. We finished part B. It was prime and composite, remember. Now we will start part C, squares and cubes. 2 to the power of 2 to the power of n plus 1 over 2. 2 to the power of n plus 1 over 2. Yes. Because 2 to the power of n plus 1 over 2 to the power of 2 is n times 2 is 2n. 1 over 2 times 2 is 1. Okay? Squares and cubes. No problem. Can I clean it? Today we are going a bit slow. Let's move on. Let me clean slowly. Okay. In this section, we'll discuss about perfect square. So there's no integer. There is no integer m such that a to the power of n is less than m to the power of n is less than a plus 1 to the power of n, where a is integer. A is integer. So let me tell you something here. M to the power of n is between a to the power of n and consecutive of a plus 1 to the power of n. There's no integer for m. For example, can you tell me any value for a? Value for a? Eight. Wow. Okay, it's your duty. 8 for n is just don't tell me large number. 4. Okay, 8 to the power of 4 is less than m to the power of n. For n is, we will use 4, is less than 8 plus 1, 9 to the... Okay. Can you hear me? I'm sorry, I lost my internet signal. Hello? Are you there? Okay. So where we left off here, 8 to the power of 4 and 9 to the power of 4. M can be here is an integer or not? Cannot be, right? M cannot be an integer. 8 and 9, two consecutive numbers, and when we take their powers, the number that between these numbers cannot be any integer. Okay. If m cannot be an integer, in this case, m to the power of 4 cannot be a perfect square. M to the power of 4 cannot be a perfect square. These numbers are perfect. For example, 8 to the power of 4, 8 squared to the power of 2 is a perfect square. 9 to the power of 4 is 9 squared to the power of 2 is same, perfect. But m to the power of 4 cannot be perfect square because m cannot be an integer. And if m is an integer, m to the power of 4 cannot be a perfect square. For m is a fraction or maybe irrational numbers, yes, can be perfect, but as long as m is an integer, m to the power of 4 cannot be a perfect square. Okay. In this section, I want to give you another special theorem for divisibility rules. You can think about this, teacher, you forgot it to give us. No, I didn't forget it. If n is an odd number then n square is congruent 1 in mod 8. If n is an odd number, n square perfect square is congruent 1 in mod 8. Can you tell me one odd number for n? 5. 5 square? 25. When we divide 25 by 8, 3 is left over, right? Yes, Sarah, you're right. 3 is left over. 3 is left over. But we have to write this remainder, right? Not divisor and quotient. Just write here as 1. When we divide 5 squared by 8, remainder here is 1. Quotient is 3. Okay. Did you get the point? So what do we get in return? You will understand what I meant to say. This part seems maybe a bit complicated for you, but actually it's not complicated. I will make it easier for you. I'm planning to solve the problems from each levels, such as easy, normal, and hard. Okay. Can I erase it? I just ask you, but I didn't receive the response. How is my voice and the camera? Tell me the quality of it. It's good. Oh, the camera is perfect. Thank you, man. Monster, where are you from? Where do you live? Nino says, yes, the video quality is good. Thank you, Nino. Where do you live? Can you tell me, please? So I can start with myself. I live in Ohrid. What about you? Okay. We will start exercise 3. The first question. Prove that 4 to the power of n plus 2 to the power of n can't be a perfect square for any natural number n. Okay. Tell me your answer. So if 2 to the power of n is a, 4 to the power of n is 2 to the power of n square, so it will be a square. So 4 to the power of n plus 2 to the power of n is a square plus a, right? So a square plus a is between a square and a plus 1 square, right? A square plus a is between a square and a plus 1 square. Let me write with details. Is less than a plus 1 square, a square plus 2a plus 1, yes. So a square plus a can be perfect square or not? Can't be a perfect square. Because, remember, a to the power of n is less than m to the power of n is less than a plus 1 to the power of, and in this case, m cannot be perfect square. So a square plus a cannot be perfect square. Of course, we have another way, but I think this way has proven that more useful for us. It's more practical, seems. Okay, don't waste of time, so please write a bit faster because I want to show you the second question as well. The second question is different from the first. We have to increase the level a bit. One hour left. Not 1 hour actually, 15 minutes left. Today maybe I will start the lesson a bit early. We will see. Did you understand the solution? Does it make any sense? Okay, the second question is coming. Is there any natural number? Is there? I'm sorry, I have to clean this part also because the solution a bit long. So the place. Let me clean beauty. Okay. The second question. Is there any natural number? Is there any natural number n for which n squared plus 2n plus 1997 is a perfect square? Okay. For any natural number n squared plus 2n plus 1997 can be a perfect square or not? We have to prove it for any natural number. Do you have any advice for the question? How to approach it? Or do you have an idea where can we start it? For example, for n is 1. 1 is a natural number. 1 square 1 plus 2 times 1, 2, 3. It is 2000. 2000 cannot be perfect square. If n squared plus 2n plus 1997, it's the perfect square on the question given us. So we say that we can start from here. N squared plus 2n plus 1997 is equal to k squared, right? It must be perfect square. Yes, you're right, Logoji. So instead of 1997, we have done before, remember, we'll separate x squared plus 2n plus 1 plus 1996 is equal to k square. N squared plus 2n plus 1 is n plus 1 square plus 1996 is equal to k square. When I take n plus 1 squared to the other side, we get for 1996 is equal to k square minus n plus 1 square, right? A difference of two squares it is. Difference of two squares is step 1 and step 2. So when we write difference of two squares, k minus n minus 1 times k plus n plus 1 is equal to 1996. But 1996, when you find here the prime factorization of it, we will get is 1 is 2 times 499 will give us 1996. Yes. 4 times 499 is 4 times 499. I'm sorry, somebody called me. I cancel it. Yes. 4 times 499 is 1996. So automatically we can say k minus n minus 1, k plus n plus 1 is element of 1, 2, 4, 499 and 998 finally itself. When you find here k minus n minus 1 and k plus n plus 1, we can use, for example, for k minus n minus 1 and 1, for the second expression 1996. For the first expression we can use 4, and for the second 499. 4 times 499 will give us 1996. Maybe the first one we use 2, and for the second we can use 998. Is same again, will give us 1996. So these two expressions are elements of 1, 2, 4, 499, 998, and 1996. Okay. So I will simplify it. I will write directly. You can try other values at home. But we have just only one solution. For k minus n minus 1 is 2, and for k plus n plus 1 is 998. I will pick it up here. 2 and 998. K minus n minus 1 is 2. K plus n plus 1 is equal to 998. At lineup, k and k cancels each other. 2k is equal to 1000, and 4k is, we will get 500. Glad to have it. For n is 497. I got it. For n is 497. So we can say n squared plus 2n plus 1997 is a perfect square for n is 497. Okay, 497. And when we write for n is 497 here, what is k? K is 500, right? Okay. So n squared plus 2n plus 1997 is a perfect square. Perfect square for n is 497. Did you understand? Is there any question? When I solve it here, actually I didn't consider all possibilities. At home is when we finish the lesson, you can consider all possibilities actually. Okay, because the time is limited. We need the time. And I have 3 more questions. Okay. Can we move on? Let's move to the moon. Okay. Yasna. Yasna in Russian language means understood. Okay. By the way, I can speak Russian language. Okay. Question 3. Solve the equation 2 to the power of n plus 7 is equal to m squared in the set of integers, so n and m integers. Okay. Okay. The equation given, 2 to the power of n plus 7 is equal to m square. So actually 2 to the power of 7 plus m is a perfect square because equals m square. So all you need to do is find the values for m and n. But don't forget it, m and n are set of integers. Okay, let's start it. If n is less than 0 for -1, 2 to the power of n is a fraction, right? 2 to the power of -1 is 1 over 2. 1 over 2 is not integer, is a fraction. For n is -1. 1 over 2 plus 7 is 15 over 2. And 15 over 2 is equal to m squared. For m is also, we cannot get integer. So we say that n is greater than 0. Integer. For n is 1. m is, for n is 1. What is the value of m? Tell me. Not m squared, m, you have to tell me the value of m. Plus minus 3, right? Okay. For n is greater than 2, for n is greater than 2, then 8 divides 2 to the power of n, right? For example, n is 3, 2 to the power of 3, n is 4, 2 to the power of 4. All these numbers, for n is greater than 2, 2 to the power of n is divisible by 8. Okay. And m is an odd number. Because 2 to the power of n is even, if n is greater than 2, for all values, 2 to the power of n will be even. Even plus 7, odd number. So odd is equal to m squared. So m is here even or odd number, tell me. Of course, m is an odd number, right? Because even plus odd number will give us odd number. Yes, you are right, Blagoje. M is an odd number, yes. Remember that if m is an odd number, n square in modular arithmetic system, when we divide by 8, 1 is left over, remainder is 1, right? Okay, so if m is an odd number, m squared is also odd number. So we can say m squared is congruent 1 in mod 8. We can say it. Yes. And what is m squared? 2 to the power of 7 plus 2 to the power of n plus 7, right? M squared is equal to 2 to the power of n plus 7. in mod 8. A 2 to the power of 7 is divisible by 8. We said that here. So when we divide 2 to the power of 7 plus 7 by 8, what is remainder here? 7 is left over. How is it possible? M squared is equal to 2n plus 7. M is an odd number. When we divide m squared by 8, we will get, for remainder, is 1. When we divide 2 to the power of n plus 7 by 8, we will get 7. But actually m squared is equal to 2n plus 7. That's a contradiction. That is contradiction. So we have a solution only there is only solution for n is 1, for n is 1, for m is plus minus 3, because if n is greater than 2, there's a contradiction, because m is an odd number, m squared is also an odd number. In division property, we know that the perfect square of any odd number divided by 8 will give us 1. So for 2 to the power of 7 plus 7 is remainder is 7, but for m squared is remainder is 1. So it doesn't provide actually. So we say that's a contradiction. So there's only solution for n is 1 and for m is plus minus 3. Okay? I want to leave you question 3. The third question is for you. I want you to solve it. I'm sorry, not question 3, question 4. Yes. I want you to let question 4. You can try to solve at home because it's very similar, like question 3, the third one. So let me write question 4. Let n be an integer greater than 9, greater than 9. Find all n is element of natural numbers such that n squared minus 15n plus 55 is a perfect square. Is a perfect square. A perfect square. Write question 4. And after that, I have got one last question. By the way, we will finish the lesson for today. I hope that the lessons are useful for you. I wish it helps you. If the lessons are useful for you, and don't forget, click like button. Okay. Thank you. Can we continue? I want to clean the solution. Okay. Did you write the question for its homework for tomorrow? Okay. So let's give a look. Question 5. Let 2 to the power of n plus n square be a prime where n is greater than or equal to 2, is a natural number prove that the number n minus 3 is divisible by 6. Yes. So 2n plus n squared is a prime number, but here is n is greater than or equal to 2. And by the way, n is a natural number. So in this case, we have to prove n minus 3 is divisible by 6. And we have to prove n minus 2 is divisible by 2 and 3, right? 2 times 3 is 6. The prime factorization of 6 is 2 and 3. So n minus 3 must be divisible by 2 and 3. Okay. So let me solve the problem with details step by step. And I will try to solve it slowly. Okay. Let's make a deal. I will solve the problem part by part. For each end of the part, I will ask you, did you understand or not? If it is okay, just say yes, okay? If it's not, say no, and I will explain again. And the first step, the first part of the solution. First, we need to define that n is odd or even. Define n is an odd or even. If 2n plus n square is a prime, n can be an or odd number? N can be just odd number because 2n plus n square is a prime. The prime numbers, odd numbers at the same time, you know? So n cannot be even, but n cannot be even. Okay, n cannot be even. So we say that n is an odd number. If n is an odd number, instead of n we can write 2n plus 1. It says n is greater than or equal to 2. So m is element of positive integers. Is there any problem here? Yes, no? Integers? I mean that all real numbers. Integers, for example, 1 over 2 we can use for m is 1 over 2, right? So we can say instead of all positive integers, all positive real numbers we can say, right? All positive real numbers, the same. But positive integers, rational numbers, instead of that we can write actually all positive real numbers because we can use 1 over 2 for m, right? 2 times 1 over 2 is 1, 1 plus 1 is 2. And start from 2. Okay. The second part, we said that 2n plus n square is prime, so m is an odd number. We will add 1 and subtract 1. 2n plus 1 plus n squared minus 1 is equal to prime a to the power of n plus b to the power of n. Remember, a plus b times k. A n minus b n is a minus b times l. So 2 to the power of n, instead of 1 we can write 1 to the power of n. 2 to the power of n plus 1 to the power of n is 2 plus 1 times k plus n squared minus 1 to the power of n, but here in this part we can use instead of n is 2 because to use difference of two squares it will be n minus 1 times n plus 1 is equal to prime. Two plus 1 is 3 times k plus n plus 1 times n minus 1 is a prime. Now look, it's important. Let me make the line here. Draw the order. Draw the border. Yes. And the third part, tell me, 3 times k plus n plus 1 times n minus 1 is a prime. N plus 1 times n minus 1 can be divisible by 3 or not? If n plus 1 times n minus 1 is divisible by 3, for example, let's say 3s, so 3k plus 3s, there's a common factor, is 3. So we will get 3 times k plus s, but 3 times k plus s cannot be prime number. So we can say, if n plus 1 times n minus 1 is divisible by 3, we will get common factor for 3, so 2 to the power of n plus n squared cannot be prime. So we can say n minus 1 times n plus 1 is not divisible by 3. 3 does not divide n minus 1 times n plus 1. Okay? Did you understand? Okay. Okay. Speaking of divisibility by 3, can you remember from yesterday? I told you 3 consecutive natural numbers. One of them must be divisible by 3. Remember, n minus 1, n, and n plus 1. The numbers are 3 consecutive numbers. Actually, 3 consecutive natural numbers. And for divisible by 3, we said that one of 3 consecutive natural numbers must be divisible by 3. N minus 1 and n plus 1. They are not divisible by 3. If they are not divisible by 3, but we know that n minus 1, n, and n plus 1 divisible by 3, one of them. If n minus 1 and n plus 1 is not divisible, so n is divisible by 3, right? N minus 1 not divisible, so n is divisible by 3, and here n minus 1 and n plus 1 cannot be divisible by 3. So we got it. It's important for us that n is divisible by 3. If n is divisible by 3, finally, n is odd number, and n is divisible by 3, n minus 3. If n is odd, n minus 3 is even or odd number? Tell me. Thank you. Yes, if n is odd number, n minus 3, n minus 3, and even. And even. That's n minus 3 is divisible by 2. Yes, if n minus 3 is even, so automatically n minus 3 is divisible by 2. Notice that. And also n minus 3 is divisible by 3 because n is divisible by 3 and 3 divisible. 3 is divisible by itself. So automatically n minus 3 is also divisible by 3. So we got the answer. N minus 3 is divisible both by 2 and 3. Yeah. I'm very happy that it ends in peace. Okay. I'm really glad to have it. To be honest, tell me, do you have any problem with the solution? No. And others, please respond. Give me the answer. No. If you need extra explanation, I can do this, no problem. Okay. It's very good sound. So I think most of you understood it. So it was the last question. So what we have done today, we have done actually squares and cubes and definitions of prime and composite numbers. We have solved exercise 3 and exercise 4. The questions were related to prime composite numbers and squares and cubes. Actually, not cubes, just squares, because in general we solve the problems about perfect square. And actually you will not see the cubes. And I think you will face the perfect squares on the competitions. Okay, anyway, I have to talk a bit less. So that's enough for today. We have finished the lesson. I wish you every happiness. Yes, like, share, and subscribe for more math lectures. See you next time. Thank you. Thank you very much. Don't forget to click like button. Everybody, bye bye. Take care of yourself.